Okay, so today we're going to go over the integrating factor method for linear function. And this is a pretty useful technique because not all differential equations are separable. For those of you who take calculus, the first, maybe Calc 1 and Calc 2, and even Calc 3, you're going to deal with differential equations where you can have the form where it's like, you have dy dx is equal to a function of x times a function of y, and therefore you can just move this to this side and do your usual stuff, because all you have to do is just say it's this, and then from there you know what to do, just integrate both sides. Now in this case that same thing will not work, in the sense that you can't. So if we have a first order linear differential equation in standard form, which is the form you're going to see above here, notice that there's no really a way to separate this. Because if we move the p of x to the right side and the y, of course, and we try to we can't isolate the functions by itself and then move it to one side in the way that we could with a separable differential equation. So there's another method to this. And so here's the rundown of what we're going to do. The first thing we're going to do is we're going to find something called mu of x. So mu of x. And we're gonna, so this is essentially equal to e to the integral of p of x dx. Now these functions right here, so the p of x and the q of x, they're functions of x. They can also be constants. Okay, so they can be like 4, 24, whatever. So just keep that in mind. And really, once you find what this integrating factor is, you're going to multiply it to this entire equation up here. So it's going to be mu of x dy dx. Then it's going to be mu plus mu of x p of x y is equal to mu of x qx. And what's going to happen here is that you're going to end up this left-hand side as a result of a product rule. So if you remember what product rule is, if you have a function, let's say y is equal to like f times g, then y prime would be f prime g plus g prime f. And that's what you're going to get here, because you can notice that we have, this is like the first step of the product rule, and this is like the second part of the product rule, where y, we have one part where we differentiated y and one part where we kept it but differentiated the other. And you're going to see this work out even more clean when we actually show it. So that's the idea behind this, and once you have that, it's pretty actually very easy to really go from here. There's not too much to worry about. So let's do some examples. So if we have dy dx is equal to, minus 4y is equal to e to the 5x. So in this case, we're gonna label our things. So we have, p of x is negative 4. We know that q of x is e to the 5x. Okay, so similar to the stuff up here, right? Here. And like we said earlier, we're going to use the integrating factor. So remember, mu of x is just e to the integral of p of x dx. And so in this case, it's the e to the integral of negative 4 dx. And this is really just e to the integral of, e to the negative 4x. And we're not going to think about the plus c right now. It's going to come back later. In a different video, I think I'll post, I already made it. I will share like the more detailed concept behind this, but this video is really just for you to understand how to actually apply this. This is like an application video. So from here, you have e to the negative 4x. Okay, so now what we're going to do is we're going to multiply that to every, term on this above equation. So it's going to be e to the negative 4x dy dx minus 4 e to the negative 4x y is equal to e to the, it's just x, because if you multiply these two together, the exponents will just subtract each other. So now we're going to be looking at this and be thinking, okay, what does this left-hand side look like? What does this look like? Well, as I said earlier, we're going to be thinking about the product rule, and this quite literally is the product rule. Notice how this is the same thing as e to the negative 4x, but it's times y, and it's the derivative of this. So it's the derivative of e to the negative 4x times y, right? Because look, if we took the derivative, we get e to the negative 4x times y prime minus 4e to the negative 4x y. So we have, we can rewrite this left-hand side as just the product rule there. And we're going to keep the left-hand or the right-hand side the same. Now this differential equation is solvable. Okay? So from here, if you just integrate both sides with respect to x, of course, the left-hand side is just going to be e to the negative 4x y, right? The integral of the derivative. And then the right-hand side is just e to the x plus c, and that's where the plus c comes from. And so our final solution is just going to be y is equal to e to the 5x, because we're moving it to the right-hand side, but it's a negative exponent. And then we have plus ce to the 4x. Okay, so this is our final differential equation. And if they give you an initial condition, you can solve for this c. But that's the solution to our differential equation. So this is the idea of the integrating factor. Now, can we make this thing a little bit faster? Yes, we can. Notice that if you think about it, the resulting left-hand integral, after you find mu of x and you integrate both sides, the left-hand side is always just going to be, it's going to be mu of x times y is always going to be equal to the integral of q of x times mu of x. That's going to be the result every single time. Right after you find the integrating factor, this step right here is, if once you're going to start to see it, you're always going to get mu of x times y on the left hand side, and we're going to see that in the next example too. So here's another problem. So if we have dy dx, and then we're going to add that by 3x squared plus y, and we're going to set that equal to x squared. So in this case, really, we're going to do the same thing, right? But what we're going to do, oh sorry, it's not plus y, it's multiplied by y. Okay, there we go. So the same thing in this case, our p of x is just 3x squared. So our integrating factor, mu of x, is just equal to e to the integral of 3x squared dx, and that's just e to the x cubed, ignoring the plus c again. We're going to multiply that by to everything on the differential equation above. So it's going to be e to the x cubed dy dx plus e to the x cubed 3x squared y is equal to e to the x cubed x squared. And of course the left hand side is just simply the product rule differentiated form of the derivative of e to the x cubed, and then we're going to tag on our e to the x cubed y, sorry. So this is really this on the left-hand side, and we have x squared e to the x cubed on the right. And so if we integrate both sides, really ignoring notation here, on your actual paper, please write the differential. It's going to be e to the x cubed y is equal to the integral of this. And for this one, we're going to have to do a u substitution, so very quickly. So we're going to we're going to have a u is equal to x cubed. Our du will just be 3x squared dx. And so this is really just the integral of 1/3 e to the u du. And of course, this is just the same thing as 1/3 e to the x cubed. So on the right hand side, we have 1/3 e to the x cubed plus c. We can simply just move everything to one side, so y is just equal to 1/3 plus c e to the negative x cubed. Okay, so this is our final answer. And once again, you're going to see that this left-hand side is just mu of x times y again, right? This is your mu of x. This is your y term, and it's the same as above because we had mu of x here. We had our y term. So your resulting left-hand side is always going to be just mu of x times y. So you're going to begin to notice this pattern. And we're going to do another problem. So we're going to do something a little bit different. So y prime is equal to x minus 2y. So in this case, before we do anything, we're going to have to actually, make it into standard form. So in this case, we're going to just simply move the 2y to the left side. So I'm going to rewrite y prime as dy dx. We're going to add our 2y, and that's just, we're going to leave the x on the right side because that's going to be our q of x. We're going to need it. In this case, our p of x is just going to be the constant before the y term. And so our mu of x is just e to the integral of 2 dx, which is just e to the 2x. And in this case, we're just going to do the same thing, where now, instead of showing the steps of the product rule, I'm just going to go straight to saying that it's going to be e to the 2xy on the left-hand side is going to be equal to the integral of e to the 2x times x dx, right? Because the right-hand side is always going to be our mu of x, and then for this, it's just our q of x. Do you see that? So we have our q of x times mu of x on the right-hand side. It's always going to be like that. And so in this case, we can just go ahead and say e to the 2xy is equal to, and then of course you can, for this integral, you can make your substitute, you can do some u substitutions, and ultimately what you're going to have to do is say u is equal to 2x, x is equal to 1/2 u. It actually doesn't really help. Oh, this is an integration by parts. Okay, so we're gonna have to do, I'm gonna do di method. We'll do x 1 0 e to the 2x 2e to the 2x, or sorry, 1/2. I think it's 1/2 e to the 2x, and it's 1/4 e to the 2x plus minus plus. So we're gonna have, sorry guys, this right hand side, it's an integration by parts problem. So we're gonna use the di method here. So we're gonna differentiate x and integrate e to the 2x. So it's gonna be x over 2e to the 2x minus 1/4 e to the 2x, and that's it. So the plus c. So this is equal to that. So we have our e to the 2x y is just equal to x over 2e to the 2x minus 1/4 e to the 2x plus c. This left right hand side is a result of doing integration by parts. And all we're going to do is just, last step, move e to the 2x to the right hand side. So it's going to be x over 2, and then it's going to be minus 1/4 plus c e to the negative 2x, and there's your final solution. So as we see, it's very powerful, and there's a lot of steps, obviously, but once you understand some of the shortcuts that you can find after doing this, it's very easy. Now before we go, I'm going to do one more problem, which is a really fun problem. So if you might see this in your class or whatever, but it's a really good problem, and it's quite tricky. So it's going to be using the same ideas, but now we're going to see how other topics from previous calculus courses are going to be applied here. So we have dy dx, and we're going to add y. That's going to be equal to 1 over e to the 2x minus 5e to the x plus 4. And what we're going to do is, okay, well, first of all, mu of x is, this is all the same stuff. This is q of x, or this is p of x over here is just 1. And this right-hand side is our q of x. So our integrating factor is just going to, be 1. It's literally just 1. So mu of x is just equal to the integral e to the integral of 1 dx, which is just e to the x. Now we're going to multiply everything by e to the x, dy dx, and then of course it's going to be adding e to the x y is equal to e to the x over e to the 2x minus 5e to the x plus 4. And the same thing, the left hand side is just a result of product rules, so this is really e to the x y prime is equal to all of this jumbo right here, which I'm just going to duplicate. Okay. And so from here, the left hand side is going to be the same. It's going to be e to the x y. We're going to integrate both sides, right? And now we're going to apply another technique that we covered, you covered in a previous calculus course, is we're going to do a partial fraction, we're going to do a substitution and a partial fraction decomposition. So we're going to let u equal e to the x, and du will just be e to the x dx. So if we apply this, what we're going to get is we're going to have the right hand side, and we're going to do partial fractions. So first thing we're going to do is, after the substitution, you will get the following result: 1 over u squared minus 5u plus 4. Okay, and this is all going to be du. So hopefully you guys saw where that all came from. And from here, we're going to do a partial fraction decomposition, particularly, so for example, it's going to be 1 over u squared minus 5u plus 4 is going to be equal to 1 over u minus 4 times u minus 1. And that's also going to be equal to a over u minus 4 plus b over u minus 1. So we're going to do a partial fraction decomposition here. And I'm going to skip some steps here because these steps are quite easy, but you're going to get a as 1/3 and b as negative 1/3. Okay. After you do that, and so really the integral of 1 over u squared minus 5u plus 4 du is just 1/3 ln of u minus 4 minus 1/3 ln of u minus 1. Okay, so that's, so all we're doing is, because we just did our partial fraction decomposition, and this is our integral, which is just basically 1 over 3 u minus 4 minus 1 over 3 times u minus 1 du. So that's how we got to this part, and we of course have our plus c. So once we make our substitutions, it's just going to be equal to 1/3 ln of, we're going to combine the differences using the properties of log, so u minus 4 over u minus 1 plus c, and then we need to now make a final substitution. So what we did there was just combine the top over there, and from here it's really simple. It's just substitute our e to the x back, minus 4 over e to the x minus 1 plus c. And remember, we're not done, because this is really just equal to e to the x times y. So our final solution comes from the fact that y is just going to be 1/3 e to the negative x ln of e to the x minus 4 over e to the x minus 1 plus c to the negative x, just moving the e to the x to the left-hand side and solving for y. And there's going to be your final little solution here. Lots of things that really happen there, but it's tough. But this is why you take those previous courses, and it's So there you guys have it. This is your final solution. I hope you guys have a great rest of your day.